that was your moment of mindfulness right there. We'll just get rolling. Unless somebody wants that, then we can do that. Do you count on that? Is that like something that like helps you in your day? A little bit? Yeah? Okay, let's just do 2 minutes. Just take 2 minutes. Let's take 2 minutes. It helps me. It really helps everybody, even if they won't acknowledge it. So, let's just take a minute and do something very basic, like just focus on noticing your breath. Very seriously monitoring every step of the breathing process. Notice yourself running out of air, or struggling in any way, you are trying too hard. Just step back a little. Let it go on its own. It up with one more round. Let's do some real analysis. Oh God, it's going to be a bad day. I was just like, where are my glasses? That's going to be that kind of day. All right, that's cool. No problem. So we have a homework that's out. Kayla already asked a question. I want to talk about it in front of everybody because this problem can be miserable or it can be super trivial. It really can be if you just look at it the right way. And there's a simple observation. Which one was this?
255.
255. So 255, they tell us that we have a sequence where every subsequence converges. Is this right, Kayla? Am I saying this?
Yeah.
And then the question is, does the original converge?
Mm-hmm.
Yeah. So one thing to keep in mind is that a subsequence can be anything. If this is the original sequence, this is a subsequence. Literally just don't look at the first term. And we know something about convergence. Convergence really has to do with the tail end of anything, right? So if I can find, so if there's some limit that this thing goes to, that this thing goes to. So we say we've got the subsequence and it converges to some A, then that means eventually I can get this less than any epsilon, so we can find some n such that this happens when, and now I'm mixing letters, but who gives a shit? That's okay. So if I can do that for this sequence, as long as n is bigger than 1, and it always will be, this statement would also hold true for that original sequence. Just remember, so the key thing, the lesson here is convergence has nothing to do with the first billion terms. Nothing at all to do with the first terms. It has to do with the tail. Tail behavior. I think that's the lesson that we're supposed to get out of that problem, Kayla. Any other questions on that homework right now? No? Cool.
Can I ask,
Yeah.
maybe, like, I don't know how, like, what you, so, for 264,
Yes.
C, can I ask what that, like, syntax means?
I think we're probably gonna have to talk about the
Okay.
stuff today. Does it say Koshi?
It's Koshy and it's like got double brackets.
Oh, right, okay.
Maybe I
So
missed
let's talk about that one first, and then we'll talk about Koshi. So forget that you don't know what Koshi is yet, but you will very shortly. Good news, it's something. It's going to turn out to be something you already kind of know, while also being one of the most important ideas of the class. So in 264, where's my bag? In 264C, oh yeah, there we go. We've got the sequence A sub n, and it's what we'll understand in probably about 15 minutes, 10 minutes, Koshy. And then they form this new sequence, C sub n equals, they use this notation. And for them, this is the ceiling function, if you've ever seen that. Have you ever seen ceiling function? Yeah, and it just basically means round up to the next integer, no matter where you're at. So for example, if a sub, well, let's just take a look at a sequence. Let's say a sub n is 1 over n. What will c sub n be here? Let's just take a minute, everybody kind of think that through. So this means the round up to the next integer. Don't use your normal rounding rules. Those aren't in play here. This is a specific rounding rule. What does that sequence look like? Anybody want to tell us? It's just constantly 1. Because these numbers here, these are all these are in 0 to 1. And literally the first one is 1. And so, even this rounds up to 1. So C sub n is constantly 1 here. And that's how I would think about that problem.
Thank you.
You're welcome. This one is tricky, and so another tip on this problem is to just think, can you create a sequence that converges on its own? So this is really what it's going to come down to. Can you find a sequence a sub n that converges? But this doesn't. And I'm going to tell you the answer is you can. So that's the big tip. That I can definitely find such a thing. And if you haven't found it yet, you haven't played around enough. Don't get too crazy. You don't need to get fancy here. Think of the different ways sequences can converge. This one clearly isn't going to do it because it turns into a constant 1 thing, so that converges. What could you do? You could even tweak this one. This one could be tweaked to be the answer. Other questions? Kayla, you're loaded with them this morning. You done? You good?
I think so.
Yeah? Okay, cool. Let's roll on with the stuff for today. We are talking today about a very specific type of sequence that will turn out to be not a new thing at all, but we have to prove that fact. So let's just get our definition out here. We say a sequence x sub n is Koshy if for all epsilon that are positive, there exists an n that is a natural, let's just say that, such that when m and n are greater than that cutoff point, so this is going to be a little bit different, we have a sub m minus a sub n. The distance between those two is less than epsilon. So just take a look at that. Read that for a second. What is different about that and our normal definition? Because it looks like convergence, right? Kind of. It's got that there exists, there's for all epsilon. How is this different than convergence? Let's just put it up real quick. Can you write that definition out? X sub n converges if, can you complete that definition? So I got two problems for you. Complete that definition. What's that? How's the difference? There's lots of different ways you could answer that question as to how the two compare. Is that lighting up there okay for y'all? It could be a little bright. Yeah, thank you.
I think
So
it
you are
looks
just
good.
like, I want you to be my manager. Can I hire you to be my life manager? Because that would be so good.
You got it, buddy.
Oh man, thank you. Awesome. I'll start looking into a funding source. There, that's a little better. All right, can anybody help me with this? Let's start at the lowest level of what we need to understand. Can somebody complete this statement for me? Michael?
I like to do converges to L, just because it makes it easy.
Okay, cool. So we do need a convergent point, right? So if there is some L, I'm down with that because it's limit. I like it.
For all epsilon greater than 0, there exists n, that's an element of the natural numbers, such that for all little n greater than or equal to big N, absolute value of a sub n minus L is less than epsilon.
Love it. Nicely done. Thank you, sir. Okay, yeah, beautiful. What's the difference? Yeah, Mike?
So I think of the regular one as all the terms are getting arbitrarily close to L, but for the first one, it's that they're getting arbitrarily close to each other, it feels like. I don't know how to say that rigorously.
No, that's beautiful. That's exactly it. Here we actually have a target. We know where things are going. Here we don't. We simply know that the terms are starting to bunch up. So they have this like, here's a sub 1, here's a sub 2, a sub 3, a sub 4, and they're just starting to get closer and closer together as we move down. And this is just a very specific example. But think about what that statement's all about. If you've got your sequence and you listed it out, and some out here we've got some a sub m, and who knows where a sub n is, that this sequence is Koshy if you give me a tolerance level for how close together I want things to be. So this distance here would be epsilon in that little gap. And I can find a place in this sequence where no matter which two terms I grab from that point on, so here's the n, no matter what I grab from that point on, any two of those terms are going to be within epsilon units of each other, no matter which ones I pick. So that's the big difference, and it's kind of a conceptual leap. But as I said, there is some good news ahead. This idea of Koshy sequence is important because sometimes we want to deal with a sequence that we don't know where it goes. We've got some sequence, we know that the terms are starting to bunch up, but we have no idea around what. So the power of being able to work with this is we don't need a limit. Whereas with the traditional, we actually have to know where things are going, and at least claim that we do. So that's the power of Koshi sequences. And we've actually got so a couple of nice results. We're gonna head toward a thing called the Koshi Criterion, which is going to tell us, it's going to characterize Koshi sequences for us in a way that's going to make life really easy. Because right now that looks kind of challenging. So let's head toward this. Headed toward. This isn't it exactly. Headed towards. Towards, who gives a shit? Put an S on if you want it. I don't know. So we've got some results that are going to get us there. This Theorem 262 is our first one. Theorem 262 is that every convergent sequence is Koshy, which kind of makes sense. But we need to get a rigorous demonstration of that. All right, so this is going to be kind of a weird proof. Suppose we have a convergent sequence. Suppose X sub n is convergent, and let's make Michael happy today that it converges to L. We all like L. We like mnemonic devices. So this. What I need to do is produce, now don't write this down because we're going to get there, but I need to produce some n such that x sub n minus x sub n is going to be less than epsilon when m and n are bigger. I mean, you can write it down if you want, but do as you see fit. So somehow we have to get rid of the limit in this statement. But to start off with, that's all we have. So let's oh, Michael, yeah, go for it. Yeah, if you got an idea, this is awesome.
I was gonna say, I feel like we've done this enough times where it feels like we're gonna make x sub m converge to epsilon on 2, and then x sub n go to epsilon 2 and pick the bigger n.
You've been awake. Yeah, that's good shit. That's exactly the game. So, did everybody get what Michael's saying? We're gonna use an epsilon over 2. We're gonna triangle inequality shit together to get things less than epsilon. So beautiful, sir. So because of this, there exists an n such that, and we only actually need one n here, which is kind of the neat cleanness of this all, such that x sub n minus L is less than epsilon over 2, and we should say out here, given epsilon greater than 0. We know that, but let's be precise. Thus, take a minute for yourself before we talk about this. Can you complete this? You've got to get an L in there, maybe 2 L's, so that this and this can be paired with them. See what you can do here. Just take a few minutes to finish this proof up. stuck, I'll give you a little tip. Tip, I guess, really. Need to effectively get a 0 in there. You want an L. This might not look see you okay, here, see your furrowed brows, Kayla. Yeah.
So next to by the triangle inequality, you've got a left center equal to, and then it changes to an equals.
Oh yeah, and this is just to change the order on this one.
Perfect.
Just it's
Got
an
it.
aesthetic thing more than an actually functional thing. Noah, can you help us complete this, sir?
You would want to do the minus L plus L.
Beautiful. And then group these together for the triangle. Yep, and then, thank you. Does this make sense how that worked? I basically inserted 2 L's, broke this down so that we had each of these terms crushing up against an L, and we got them within, so I pitched, this is L, here's epsilon plus epsilon over 2, here's minus epsilon over 2. We got all the terms, right, we're doing this. We don't know what's happening there, but we do know that at some point, n, no matter what x of m I pick, so if this is x of m right here, this is x of n right here, that the distance between those is no wider than the distance of this tube, which is epsilon units. Cool. And any questions on that at all? Good. All right, so what we would like, here's the punchline. It's going to turn out that the converse is also true, that every Koshi sequence is convergent. And that is the Koshi criterion. That there's no difference between saying something in the real numbers only in the real numbers, because there's places where this isn't true, but they're fancy function spaces that infinite dimensions and all sorts of stuff like that. But we want to show that to say something is convergent is the same as saying it is Koshi. And then that makes our life a lot easier. Why? Because sometimes it's actually easier to show something's Koshi. Especially if you don't have a candidate limit. You can just show that the terms are starting to get closer and closer together in the tail. And then you can say, oh, this is Koshi, therefore it does converge to something, and now I can claim there's a limit. That's the power of Koshi. You don't have to pretend you know something you don't know. So, we want the converse of this. But it's going to take a little bit of work. We need a lemma to get us there. We want the converse, in other words, Koshi implies convergent. Otherwise, it's not helpful. It's just like, oh, convergent sequences can be called something else. This means they're the same. Okay, so we need a lemma. Maybe, I don't know what they call this. Oh, they call it a theorem. This is, oh no, they call it lemma 263, good. My instincts were right here. This lemma says that every Cauchy sequence is bounded. So we're working our way up to this, much trickier. All right, so proof. Take a Cauchy sequence. We've kind of proved something like this before. So I'm gonna start us out and then let you see if you can take this home. Let this be Cauchy. Therefore, given, how about this? We'll just say epsilon equals 1. Pick a nice epsilon. We don't have to like worry about what its value is. That's a lovely 1. We can find an n. We know that's a natural, such that x sub m minus x sub n is less than 1 when little m and little n are bigger than big N. So my challenge to you in the next take a couple minutes is, can you convert this into a statement about just x sub m or x sub n, one of the two of those? Can you get some information about one of these two terms being less than or equal to something else? So take a minute, just see what you can get there. You might need to look at some of the variants of the triangle inequality. Run to the restroom. I'll be right back. Anybody think they got some moves for us? Dude, yeah, cool.
So the absolute value of x sub n minus x sub n plus x sub n
Oh wait, so you're saying
is equal, or yeah, sorry. Oh wait, sorry. Okay, so the absolute value of x sub n
Oh, gotcha, okay. Oh, I see, okay.
is equal to the absolute value of x sub n minus x sub n plus x sub n.
Okay,
That is less than or equal to x sub n minus x sub n plus, yeah.
Oh, I like this, Kayla.
And then from this, we know that the absolute value of x sub n minus the absolute value of x sub n is less than or equal to the absolute value of x sub n minus x sub n.
oh, hell yeah, exactly, nicely done. That is absolutely the move we need. Because, so I would put this, little note that. So, if this is less than 1, then this is less than 1, and we've got what we need, because now we can actually pull something to the right. That dude right there. Less than 1, i.e. Very nice, very nice. So the problem here is this thing is moving, right? This is going to change with the value of little n. And we want to, when you come up with a bounded thing, we want to have a statement like this. We want a constant over here. So here, I'll just give you the tip, because unless anybody has a sense of where we could set this so that it's fixed.
Could we set it to like n plus something or no?
When you say, can you elaborate?
So like x of n plus 1 or something? And then it's like
Yes, specifically this capital N. So this is fixed. This is a quantity we've already determined. It came from the Koshy part of this. So we can find this capital N. So check this out. And this is something we haven't really talked about, that this definition here, these things can be equal to N. So you could take this and say, well, that implies that this is also true. Just fix the little n at capital N. And that still is part of the Koshy definition. So in other words, everything past that n, that capital N term, so we've got this, here's capital N, here's your x sub capital N, that from this point on, no matter what term I pick out here, x sub m, that's going to be within epsilon of that little guy, or that first place where this happens. So, and in particular, let's make this really clear here. When m and n are greater than or equal to capital N, that's true for all of them, but in particular, fix little n equal to capital N. And get x sub m is less than 1 plus x sub cap n when m itself is just bigger than or equal to n. We're almost done. We're not quite done, because this is only a bound. So let me see, maybe you can help me out with this now. This is only a bound from when little m is bigger than or equal to cap n. So here's cap n, and we know that we're good and bounded out here, so we're done out here. I don't know about, yeah, Michael, what do you think?
There's a finite number of terms on the left, so there exists a largest one.
Absolutely. Nice. So we've dealt with the infinity part, right? Very stealthily, very adeptly, have knocked out the infinity part. The rest of this is just a finite number of terms. And so there is a biggest one and a smallest one, because it's a finite number here. So set capital M equal to the max. So now we're going to do a max, because we can. And you'll see why. Because first off, I've just got absolute value of x sub 1, absolute value of x sub 2, on up to absolute value of x sub n minus 1, big N, comma, this thing that bounds everything else. So certainly one of these bounds the first n minus 1 terms, and this one bounds the rest. And everything has to be bounded by one of those then, at this point. So that x sub n is less than or equal to m for all n. And we've got a bounded sequence. Kind of some cool tricks in there, some things we've seen before, put together in just the right way. All right, let's get the big result now. So this is our first step. We now know that every Cauchy sequence is bounded. Start thinking to yourself, what do I know about bounded sequences and convergence? What results do we have that help us if we know we're bounded? You just keep it off, Ashley. Jeez, we're getting ready. I'm like so ready to just rip this thing off anyway. There is no worries. We're all friends here. Oh yeah, and I guess by the way, we're supposed to establish some classroom policies for next week when we're maskless. I think we have them. We don't have any. We'll just show up and you can wear a mask if you want. You don't have to if you don't want, right? Everybody's good. If you feel at risk, there's plenty of room to move away from folks. I will not be wearing one come Monday. Super grateful. Okay, so, final result. If x sub n is Cauchy, x sub n converges. This is the other half. Those two results together give us the Koshi criterion that convergence and Cauchiness are identical in the reals. Okay, so we got this. All right. So proof. We better go with what we just paid for right off the bat, right? So x sub n is Cauchy. So by lemma, whatever, what was it, 263? It is bounded. Cool. What are the theorems we have that help us with convergence and boundedness? So far there's two. What are we thinking, Kayla?
The Bolzano wire stress says that every bounded sequence has a convergent subsequence, and then theorem 255 says that if your subsequences converge to some limit, then your original sequence must also converge to the same limit.
Pretty good. Yeah. So, yeah, and we could go back. I was thinking monotone convergence theorem, which is bounded monotone sequences converge, but you're working like a pro at school. We just literally covered Bolzano-Weierstrass on Monday. It makes sense that it might rear its head today. So, yeah, Bolzano-Weierstrass. So we have a bounded sequence, thus by the Bolzano-Weierstrass theorem. There is a subsequence and we'll say x sub n sub k that converges. And hell, since once you know something converges, just give it a name. Let's say x sub n sub k converges to L. And that's going to make life easier. So now we just need to show that the entire sequence heads here. We got to show that if I take an x sub n minus L, I can somehow get that less than epsilon. So let's let epsilon be greater than 0. And note something we're gonna hack our way through. Suggestions. There's a trick that we've done almost every week. We've done it today.
Yeah.
Yeah, right? Yeah, we've got some triangle inequality that we need to produce, but what are we going to produce it with? What are we going to add and subtract?
Epsilon over 2.
What is that?
Epsilon over 2.
Definitely, we're going to go for epsilon over 2. Yes, yes, yes. So let's actually do this part and get our way there, Noah. So let's work this through. We're going to note this, and then we'll pull out our epsilon over 2's. But let's first get this into 2 pieces, and then do it. But you're absolutely right. And then we're going to make this less than epsilon over 2 and this less than epsilon over 2. But let's get the hard part done. And let's fill in some details. Okay, look. Yeah. Yeah. Okay.
Feels like we're gonna use the x sub n sub k.
Seems like we ought to. Yeah, right?
With
Yeah.
Koshi, so they get arbitrarily close for the left one, and on the right one they go to L, which will give us 0.
Yeah. Because this is literally, we can get this less than epsilon over 2 because of this. So we can find a place where this thing gets small. Why can we make this thing small? Because it is freaking Koshy. And if this n and n sub k are sufficiently far out, we're good to go. So, nice, that's the key right there. Note this. Now, and let's give this a name. Let's give it some equation number. I'm going to call it star. Now, since x sub n is Koshy, we can find. And now we're going to actually pick a couple different n's. For this one, we definitely need a couple. We can find an n1 such that x sub n minus x sub n sub k is less than epsilon over 2 when n and n sub k are bigger than n. And you could make that k bigger than n, because remember that n sub k is always bigger than or equal to k. So if you used k here, that's also legit. This is probably a little more intuitive than this. Like just putting this here is what I'm saying. You could do that, and that's okay, but let's do this for clarity. And since it converges, oh wait, no, not converges. Since x sub n sub k converges, and since x sub n sub k converges to L, we can find an n2 such that x sub n sub k minus L is less than epsilon halves when n sub k is bigger than or equal to n2. This should have said n1 over here. So if we just pick the max of those two, right? So we're just going to say little n set big N equal to the max of those two cutoffs. And then we have x sub n minus L less than epsilon over 2 plus epsilon over 2 is epsilon when little n is bigger than or equal to our new final cap n. And we've got convergence. That's it. That's like all we're really going to prove today. But let's talk about what we just did and summarize it, at least for your notes' sake and your brain's sake. This result and theorem 262 give us the Koshi criterion, which says, in the reals, convergent sequences and Koshi sequences are indistinguishable. All right. And I think that we should maybe take the rest of the time to work on the homework while we're here together. Because that's kind of all I want to say about Koshi sequences until you actually think about them on your own. So there's two problems on the homework set that are Koshi related. And now that word makes sense, right, Kayla? So now that's like, okay, cool. And the good news is it's exactly what you already knew. Just a new way to characterize it. Diana, did you need that assignment or did you get it?
I got it.
You got it, awesome, cool. So I am available for consultation. Michael, have you heard back from anybody yet?
I got an email from Georgia Tech that they like wanted separate documents from what was on the application. They're like, we read it with great interest. We want some more.
Oh, cool. That's
I
fantastic.
got a callback. Right.
Not yet completely. They just want more stuff, but
Yes,
other than
yeah,
that,
yeah.
It's a good stuff.
That's a very good sign. Because they're not going to waste their time
Yeah.
if they're not at all interested.
If it makes you feel better, on an application I indicated that I'm a part-time student and I'm taking 18 credits. So I was like, shoot. So they called me and they're like, are you actually a part-time student? I was like, no, I promise you I'm not a part-time student. But it was kind of a funny conversation.
Yeah. Normally you do 36, just
Yeah.
this semester.
This semester, I took it easy.
Yes, sir.
That, homework that we talked about last time, homework 3.
Yes. Oh wait, so what did we talk about with it? Sorry.
Just that last time you gave it out, I wasn't here, and you said it was probably on.
Oh shit. I don't think I did anything about that clearly, Michael. So let me check my bags again, and then let me send myself an email, because that's the only way I'll remember. I'll write it on my arm or something. Yeah. Okay, I'm gonna email myself right now. Oh yeah, this wasn't my Brave Space sticker either. I don't know whose this is. I got mine still. We probably killed the recording.
Oh.
Oh no, it's okay. You don't worry. You are not responsible for this. Oh my goodness.